All right, let's go ahead and run through the information for Lab 3. Very first thing that's on here is Newton's second law. This can come in a few different formats. The main one that we talk about the most is just this equation format, force equals mass times acceleration. Occasionally we'll see it as net force, meaning if there's multiple forces, how they interact, add, cancel, whatever they do. And sometimes we'll rearrange for acceleration and we'll say acceleration comes from net force over mass. So Newton's second law specifically, if there's an unbalanced external force, then there's going to be an acceleration. You can have forces, but if they're all canceled by something, then there will be no acceleration. Sort of like when you set your cruise control in your vehicle. There are forces driving forward from your engine, and then there are forces coming backwards in the form of wind resistance and resistance in your tires and so on. And so you'd have no acceleration when you set your cruise control because you set it at say 70 miles an hour. You're going to keep going the same speed. Okay, then another formula that's going to be really important for us, something that we're going to see a lot in this class and use several times in this particular lab. Weight is equal to mass times gravity. Now, weight in the metric system is measured in newtons. And a lot of times people think that it's measured in kilograms because of how we talk about this in normal conversation, but that's actually wrong. Weight is measured in newtons. You can probably guess who that's named after. The proper mass is kilograms, right? And so when we talk about different types of masses, we can have grams, but they're very, very small and often not useful. So our better unit for mass is kilograms. And so also looking at that information and turning it the other way, when somebody's talking about kilograms, they're actually talking about the mass of the object, which may or may not be something that you knew before. Okay, then last major formula I think we're going to need today. We've got that the force of friction is equal to mu times normal force. So mu is a Greek letter. MU is the name of it. If you were to spell it out, it's kind of like a U with like a tail on the front. Changes a little bit depending on font and handwriting, but that's for the coefficient of friction, and so that is listed out here. Normal force is the force of a surface not breaking. So if you rest a weight on a surface, then typically it's going to be the same amount as the weight, but it's pushing back up to hold the weight to give it support. For our purposes, the main way we're going to end up using this formula is to calculate mu, the coefficient of friction between a board and a block. And so mu, was my attempt at drawing mu, and Adobe spiked my handwriting when it was trying to fix it, but that's supposed to be one of these, is going to be equal to, so if I get mu by itself, normal force has to move and go away. So this will end up being the force of friction divided by normal force. What's a little bit tricky about this lab is that we can't measure either of these things directly. We have to measure them sort of backwards by using other information. So we can guess about normal force by finding the weight of an object, and technically it only works on a perfectly flat level surface with no other forces involved. So it's never really quite perfect. And then friction we can't really measure, but if we can balance it out, basically find the force that it takes to cancel friction, then you can work backwards and guess what it might be. So, you can use money sometimes as an analogy. If I don't tell you how much money I have, but I say I'll be completely broke if I spend, say, $100, then you could work backwards from that and say, oh, well, he must only have $100, something like that. When we find mu, I'm just going to make up a number here. So let's say that we had 2 newtons of friction force and 4 newtons of normal force. Then we'd end up with a mu value of 0.5 and no units on them because we'd have newtons divided by newtons. As it turns out, 0.5 is actually a relatively high value for friction. A lot of times they're in the point like 0.100 to 0.300 sort of range, but there are lots of available options. Okay, so with this lab, we would want to first find the mass of a wooden block. And the wooden block is usually between like 50 and 70 grams. It'll vary a little bit. Because we're going to find this using a triple beam balance, then we need to remember, and this is similar to what we talked about from the first lab and even the first pre-lab, but the triple beam balance, anything that comes off of there is going to be 2 decimal places. The precision is 0.01 grams. So we talked about 0.01 centimeters being from the rulers, and I think I made a mention then that the balance worked the same way. So that's something we will want to keep in mind. So if I measured a block, I'm just going to make up a number so we can, use the example and see. But let's say that my block was, I don't know, 65.65 grams, because why not? Then that fits. That's the 2 decimal places. That's the G for grams. That's my format. That's what I'm going to want to see. So my accuracy, we had this definition on the first lab. Accuracy is your number of significant digits. If I look, there's 1, 2, 3, 4 significant digits in that. And that's important because then if I convert this into anything else, then I need to make sure that conversion has 4 significant digits. Let me replace the number then. So instead of just saying number of significant digits, we know this one is 4. So accuracy is 4 significant digits. Precision, I already listed out in this other spot. So just to be concise, I'll use that spot. And there's our precision. Then let's think about how this might change, right? So it says in the instructions that we have to add 500 grams on top of the block. As it turns out, the block itself is not heavy enough to run the lab. So we need to put 500 grams on top of it. All right, that is eventually going to be information we need down here. So I'm going to go ahead and squeeze that in. So if we have 565.65 grams, then that would be the block and the added mass. Okay, and then we want to remember, even if we were to put this back on a balance, we're still, looking at the 2 decimal places there. Our accuracy, though, has changed. Accuracy means number of significant digits. This thing now has 5 significant digits, even though it still has 0.01 gram precision. Okay, then now I want to convert this into a weight. So notice the labels on here, these clues, those are grams. Grams we can measure from the triple beam balance combined with the mass that's on top. If we wanted to, we could put that back on the balance and check it. But we want to see this as a normal force because that's part of that friction formula. And so this is a conversion that we're going to need to do it. And this is part of why we have to understand accuracy and precision. Because if I have 5 significant digits before I convert, then I need to have 5 significant digits after I convert. So, we're going to see how that's going to change and what things will stay the same. So for the first part, 565.65 grams. Then stick that over 1. Technically, grams are not our preferred kind of mass, so we need to do a conversion with that first. 1 kilogram, kilo or K means 1,000, is 1,000 grams. So a kilogram to 1,000 grams. And then technically this isn't a pure conversion, but it works because we're on Earth. We can also say that 1 kilogram, because of Earth gravity, can turn into 9.8 newtons. So when we have this, we can chain together these conversions as much as we want to, and that's really handy, especially when we need to convert multiple things at one time. When we multiply everything together, we multiply all the top stuff together, and then we divide each of the things off of the bottom. And then what's nice is that we've specifically engineered this, that the units are going to cancel, and they're only going to leave the stuff that we're looking for. Now we trust that the 1,000 grams is perfect because it's part of a definition. We trust that the 9.8 is perfect because we're treating that as a conversion. The answer we get from this is 5.54337 newtons. But here's the thing, that's got a lot of numbers in it. This, what I was converting from originally, had 1, 2, 3, 4, 5 significant digits. And then that means that when I convert it, when I find this weight here, I still need to have 5 significant digits. So I need to use normal rounding rules to fix this. So extra place, that 7 can't stay. So I will have 5.5434 because the 3 will round up, and then newtons. Okay, so this is still 5 significant digits. That stayed the same. But notice that my precision changed, because now once this is in newtons, my I'll label these so they're easier to see. Our accuracy is 5 significant digits, but our precision changed to 0.0001. Notice 1, 2, 3, 4 decimal places, because that's what we kept, newtons. Okay, so that's the first half of the information we need. What we found with this, and we found the weight that's sitting there, that's going to end up being the normal force when I'm thinking about my formula, because eventually I'm trying to find a coefficient down here at the end. So, you know, I guess I can spoil it now. Eventually, we're going to calculate a friction force, and then we can put these things together to find an answer. So we're getting there. From this lab, we have a pulley that runs off and hangs a string down the side of the table. And from there, we have a mass holder, and we can stack masses up on top. So the mass holder itself is 50 grams. And so say I have 112 grams. Oh, I guess we can just do it here. So say I had 112 grams, and then the holder itself is another 50 grams, then I would have 162 grams. Accuracy here, if we check our total numbers, this is only 3 significant digits. There are no decimal places because I don't have like half grams and quarter grams and 0.1 grams of mass in little plates. Those are just way too small. So these are only as whole numbers. So accuracy, I'm going to abbreviate because I'm a little low on space, but accuracy is 3 significant digits. My precision in this case is just 1 gram. If we're going to convert this into weight so that we can finish finding our friction information, then the process is the same. So let's move in and do it down here. We'll have 162 grams, stick it over 1. Then we can actually sort of combine these conversions. Notice that the kilograms cancel from both of those anyway, so it's a little bit uncommon, but we can technically say that 1,000 grams turns directly into 9.8 newtons. That just skips the conversion in the middle. It's the same work. If you don't prefer to do it this way, then you can stack it like we did the other one, but it should give you the same thing. It's a little more direct. I think it's easier to do this way, but it's up to you. So we would multiply the numbers together on the top, and then we would divide by 1,000. Order is not super important there. You just can't swap your operations. All right, but what this gives us is 1.5876 newtons. But then we want to go back and double check. We've already said that our accuracy is supposed to be 3 significant digits, right? We converted from something that had 1, 2, 3 significant digits. So my answer here needs to have 1, 2, 3 significant digits. So after the 8 is a 7, we would use normal rounding rules, and this would turn into 1.59 newtons. So on this one now, our accuracy stays the same, 3 significant digits, but our precision is 0.01 newtons. All right, I'm going to move that over. It's going to bug me. 0.01. There we go. Okay, and actually, we have all of the information necessary to go back and find a mu value. So from our formula on the previous page, mu was the force of friction divided by the normal force. Well, we got those numbers. We had to work to calculate them, but we have these things: force of friction, normal force. And we would run and do multiple trials for this, but I'm just going to do the one example. So the mu value that I don't know, I've got enough room, I'll squeeze it into the box, but we'll take 1.59 newtons divided by 5.5434 newtons. It's definitely going to be less than 1, so it'll start with a 0. Keep in mind that the newtons from each of those will drop off, so there are no units on this. And we get 0. Looks like 287. Okay, and that's how we would run through the process. For remaining trials, when we're running through, and if we're doing the hands-on lab together, then what happens is we add another 200 grams, so this would turn into 765.65 grams. Then you'd have to balance and see what this is going to be. Then the next one maybe 965.65 grams, and then again you'd have to balance and see what it takes to actually to work out here. And then you find different friction numbers. So let's say that we got 0. I don't know, 292 and 0.284, because why not? The average mu value is going to come from going and just taking a normal average. So if you've got 3 values, you want to find the sum of those first, add them all up, then divide by 3. When you do that, you'll get 0.287 and a bunch of repeating sixes. But if we look at what this comes from, so again, tracking significant digits and looking at these, 1, 2, 3 decimal places, 1, 2, 3 decimal places, 1, 2, 3 decimal places. It means that I don't want to have a whole bunch of extra sixes on the end. I'm going to round to 0.288. And I believe that's every different combination of things that you need to know. I do want to give you one little tiny hint for these. Sometimes it can help you to double check your work. But because of the way that everything is under the influence of the same gravity, gravity's not going to be different from on top of the board versus hanging off the end of a string, then technically you can find your friction directly by taking your mass on the holder plus the holder. So don't forget it needs to have that 50 grams with it together, and then dividing by the total mass sitting on the board. And that will actually give you the same number. Plus or minus a little tiny bit. So occasionally with some rounding error, the very last digit might be different, but that's not usually enough of a problem to really cause any further issues.